Okay, we're continuing on our discussion of power series, and the question at hand is, for which values of x does the power series centered at A converge? In the last video, we knew that it did converge at its center, so we already know that there will be at least one x value for which it converges, and that's x equals to A. Now, to define the others, so we are going to outline a strategy here. To find all other values of convergence, we will do two things. We will explore using the ratio test, and then we'll have to come back and check endpoints, and I'll explain all of those as we go. Okay, so those are the things that we're going to do to find the answer to our question that we want to know. Okay, and I feel like we will do this with a particular example because that is often easier, okay, to talk it through that way. So here's an example. Here's going to be our power series. We'll say 3 times x minus 2 to the n over n, okay? N equals 1 to infinity. All right, so if I were to identify all my pieces, c sub n is 3 over n, and my center is 2. Okay, so I already know off the bat that my series will converge for x equals 2. All right, so now we're going to explore the ratio test. And remember what the ratio test said. It said if the limit as n goes to infinity of the nth plus 1 term over the nth plus term, the absolute value of that is less than 1, then the series converges, right? So we are going to force our series to converge and solve for the x's that make that true. That's only going to tell us what happens when it's less than 1. So this is where the endpoint. So that's as far as the ratio test can get us. If, remember this, the limit as a sub n plus 1 over a sub n equals 1, then we don't know anything, right? The series could converge or not converge, and the ratio test isn't going to help us. So that's where we now come and check endpoints. Again, I will explain further as we look at this example. Okay, so let's apply the ratio test to our series. We'll go to a new board. I'm going to rewrite our series here because we need to. Over n, right? N starting at 1 to infinity. Okay, so we're going to be looking at the limit. So let's just write our terms down. So a sub n is 3 x minus 2 to the n over n. And the nth plus 1 term is 3 times x minus 2 to the n plus 1 over n plus 1. Right? That's what it is. So now we're going to look at the limit as n goes to infinity of 3 x minus 2 to the n plus 1 over n plus 1 over a sub n, or times 1 over a sub n. So, divided by a sub n is multiplying by 1 over a sub n, right? So it's going to be the reciprocal, n over 3 x minus 2 to the n, and we're going to force that to be less than 1. All right, a couple things we can do. We see we can cancel those 3's, and we have cancel all of those with most of those, but leave behind 1 power of that. So now we have, I'm going to group terms, the limit as n goes to infinity of 1 factor of x minus 2, I'll put that in parentheses, times n over n plus 1, less than 1. Okay, since this limit is dependent on n, we can remove the factors that are not dependent on n. And we got to take the absolute value bars with us. So the absolute value of x minus 2 times the limit as n goes to infinity of n over n plus 1 is less than 1. We're looking for the x's that make this statement true. We see that limit goes to 1, so really our left-hand side becomes this, and we're trying to solve this. All right? Now, this expands to less than 1, bigger than negative 1. That's just our algebra. So x is less than 3, bigger than, if I add 2 to both sides, 1. Okay? So if I were to come over here and draw what that interval looks like, 1 is on the end, and 3 is on the other end. And the center is 2, which we already knew was, that was a convergent piece. And it should be in the center of our interval. Okay, now, what happens, so let's come explore this and see why it's the endpoints. If I said, well, what about the x values for which this limit over here, which reduced to, let's write it down here. Everything will act the same way, except instead of less than 1, I'd say, what about when this limit n to infinity n over n plus 1 is equal to 1, right? That's the inconclusive part of the ratio test. That still goes to 1, so this is equivalent to saying this, which is equivalent to saying this. Sorry, it's not equivalent to saying that. It's equivalent to saying x minus 2 is plus or minus 1, which means x is 1 or x is 3. And those are precisely the endpoints. So all this tells us is the ratio test only tells us about the interior part of that interval. We need to now do something else to test what happens at 1 and 3. We know outside of this interval it diverges, right? Greater than 1 it diverges. So we want to find out what happens at 1 and 3. So we're going to plug those in and look at them one by one. Okay? All right, so I'm going to have to rewrite my series one more time, just so I can keep it in my head. 3x minus 2 to the n over n started at 1 to infinity. Okay, so we were at 1 and 3. Our center was at 2. So we're going to first look at when x is equal to 1. Okay, then our series becomes 3 over n, 1 minus 2 to the n, right, which is 3 over n, what is that? Negative 1 to the n, right? And starting at 1. Okay, hopefully, well, that 3, what does that do? It just scales it. So if I moved it out here, that's really 1 over n minus 1 to the n. And that is the alternating harmonic series, which we know converges. Okay, so coming back up here to my interval, and it's actually called my interval of convergence, always centered at the center. It does include the left endpoint. All right, now we need to check the right endpoint. So when x is equal to 3, we plug that in, we get the summation of n equals 1 to infinity, 3 over n, this time 3 minus 2 to the n. Again, I can pull out that 3, and now I'm left with really just 1 to the n, or 1 over n. Okay, this is the harmonic series, which we know diverges. All right, so it doesn't converge at 3. So our final interval of convergence is 1 to 3. And our radius, well, that's going to be from our center out to one side of the interval, is just, so here it's 1. So our radius of convergence is 1. Coolio?